Okay, so for freely falling objects, we have two equations. Actually, let me go back to this. So the first equation, d equals 1/2 at squared. Remember, that's general. Okay, so any acceleration, that could be a car driving down the street accelerating. Of course, remember, acceleration could be positive or negative. And the other equation that describes how the velocity changes with time when there is an acceleration is this one. The velocity is the acceleration times the time. Okay, so these two equations are general. Now, for free fall, we have a situation where the acceleration is known. It's a known value. As long as you're on the surface of the Earth, the acceleration is 9.8 meters per second squared. So that's a known value. And that changes these two equations. If you're talking about freely falling objects, remember, it's not just falling. I know it says free fall, but these are for objects that are either rising, you've thrown the object up in the air, it loses contact with your hand. The moment it loses contact with your hand, there are two equations that describe the motion. So, and of course for objects that are just falling, these two equations equally describe the motion. The distance changes with time in the following manner. The distance is equal to 1/2 the acceleration due to gravity from the Earth, little g, times the time squared. And then the velocity changes with time by similar to what we had above, but now its velocity is equal to g times t. Okay, so that's how those change. So here, let's get back to this. Alright, so we just had that. That's just showing some examples. Well, I'll do some actual examples in a little bit. Compound motion is when an object is moving both vertically, so those two equations that I just showed you, and then horizontally, where the equation is simply the velocity is the distance divided by the time. So in the horizontal direction, that would be the equation that describes the motion. As long as there's no acceleration, velocity is, well, let's be fully descriptive. The velocity is equal to the change in the distance divided by the change in time. Okay, so that's projectile motion, what's called projectile motion. The thing about projectile motion is the horizontal direction, or sometimes that's called the x direction, and the vertical direction, sometimes called the y direction, are independent of each other. And so when you combine the two motions, you get a parabolic path, like the arrows in this picture. The arrows are both falling vertically, and you can see that the little arrow that represents the velocity is increasing as time goes on. But notice the horizontal arrows don't change. So here's a very typical demonstration that we would do in class is not with arrows, of course, but if you had an arrow and two arrows, let's say one dropped like this guy is doing right here, and one shot both from the same height at the same time, they would actually both hit the ground at the exact same time, because vertically they're falling. One happens to be moving horizontally, but since the two motions are independent of each other, they both fall at the same rate. Okay, so here's another example with a football. Here's somebody throwing a football. The vertical motion, you can see the little arrows get smaller and smaller, and then right at the top, the football has no vertical velocity. The velocity at the top is 0, and that's going to be very important for a lot of the problems that we're going to solve. And then the velocity changes direction, so from the top then it starts to go down, and you indicate that with the velocity going down, and then as time goes on, the velocity in the downward direction gets greater and greater. So it gets smaller and smaller going up, 0 at the top. So I'm talking about the vertical velocity, and then after the top, it gets greater and greater, and then if this guy catches the ball from at the same height it was thrown, the velocity in the vertical direction will be the same. At least the magnitude will be the same. Notice the directions are different, are exactly opposite. But look at the horizontal velocity. Horizontally, as the football goes over this parabolic path, that doesn't change at all. Okay? These are Newton's 3 laws of motion. Let's see. So that's actually not Newton's dates. Newton was born in 1642. Not that that's really a big deal here. Anyhow, these are the dates here for Galileo. But this is actually what Isaac Newton did. He developed what's called the 3 laws of motion. He also developed the mathematics of calculus and the law of gravitation. And the central to that is this idea that force causes changes in velocity. All right, so here's Newton's first law of motion. Let's just quickly go over that. It's also known as the law of inertia. It says every object retains its state of rest or its state of uniform straight line motion. So if it's moving along in a straight line, like a ball rolling along a table or something like that, as long as there's no net force acting on it, that's what we mean by an unbalanced force, no net force, it'll just keep moving in a straight line forever. Well, unless it's going to reach the end of the table and then things will change. But, that's when that happens, of course, new forces are going to be acting on it. So this is the law of inertia. The greater the inertia of something, the greater it resists changing its motion. And really, it turns out that this idea of inertia is very much related to the mass of an object. For example, let's take 2 people on a bus, or one person on a bus and then another person on the bus. When the bus is at rest, the person is just standing there, and all of you have probably noticed this. For example, in a car, or if you happen to be standing in a bus, when the bus goes from rest to having some velocity, the moment that's taking place, you feel like you're being pushed back all of a sudden, and all that is your body resisting that change in motion. And also, of course, this is the same kind of thing. I mean, you don't have to be in a bus to notice this. If you're making, let's say, a left-hand turn, a right-hand turn, you feel your body pushed in the opposite direction because your body wants to keep going in a straight line, and the side of the car or the side of the vehicle comes up to meet that, and that's why it feels like you're being pushed in the opposite direction that you're turning. The second law is the net force is equal to the mass times the acceleration. The mass is in kilograms. The acceleration is in meters per second squared, and the force, of course, is in units called newtons. We'll do some examples with that shortly. This is the one that is usually used, and interestingly enough, this formula is, or let's say the first law of motion is a simplified version of the second law, and what that is when the acceleration is 0. When the acceleration is 0, if you think about it, all the forces add up to 0. And so there can be forces acting on an object, but they add up to 0. So the only way that they can add up to 0 is you're going to have, first of all, you'd have to have more than one force, right? And some of those forces have to be negative in such a way that the total force when you add them up, adds up to 0. I'll do an example of that a little bit later. And this is just a demonstration of the second law. I'm going to skip this. Now here's the thing about weight. Weight is a type of force, of course, that comes from gravity, and so the weight of an object, and it's a vertical force, right? It points down at the center of the Earth, is the mass of an object times little g, because that's the acceleration due to the mass of the Earth. The gravity of the Earth is pulling on every object on the surface of the Earth, and the weight of something, which is also in newtons, is equal to the mass of an object in kilograms times 9.8 meters per second squared. So in this formula, g is always, as long as you're on the surface of the Earth, is always 9.8, and the weight is newtons, and the mass is in kilograms. So if you know the mass of an object, you can calculate its weight just by multiplying whatever the mass is times little g. Now the third law of motion is very different from the other two. The third law is not about the same object. So it's when two objects interact with each other. So if I push on the wall, for example, the wall pushes back on me with an equal and opposite force. And so that's really what the third law is all about. And the thing about it is it's two different objects interacting, and the forces are equal and opposite. I'm going to stop right here. We'll pick it up a little bit later, this idea of momentum. All right, let me stop this.